2 7 squared plus y squared equals 25 squared, and you get y equals 24, and then you put 24 into the equation, and then you do algebra, and you get negative 0.58, or on the thing it said negative 712.
Same thing.
Yeah.
Yeah.
They did it weird on the answer.
How so?
Like they put it into fractions.
Oh, they did everything as fractions instead of like a decimal at the end? Or
It's like they differentiated it into negative 2x over y, and then they put
that's a dumb way to do it. I like your way. This works. This is the way I taught it. I don't know why Donna did that with her key. So I guess you were using y instead of h, and it looks like we all used y, so we'll go ahead and change that in the problem. There, and there, and there. All right, so this is just a Pythagorean theorem problem. You take the derivative, and you also need to find out what the height is right now. So you use the Pythagorean theorem for the given x value, and once you have that value for y to find the current height, then you can solve for the speed at which I'm falling down the ladder. In part 2, now you've continued to pull this base away from the house, and so now x is up to 15 feet, and so we want to see, okay, are we falling at the same speed or are we falling faster? So who did part 2? All right, so Rachel, talk to us.
So to get the y, in order to plug into the equation, I did 15 squared plus 1 squared equals 25 squared, which is 225 plus 1 squared equals 625, which gets to 1 squared, and then y equals 20. And then I plugged y into the equation, I got 15 times 15 is 20, negative 30,
All right, so you seem to have gone with the answer key route of dy dt equals something. So that's the answer you got. So for dy dt, you then isolated it. Yeah. So Grace kind of kept this equation, the derivative as is, and didn't bother like solving for dy dt. You seem to have taken this and then isolated the dy dt. So for people who didn't do it that way, just to show what's going on, I guess you plug in the 2 for dx dt, so this is 4x. So you would subtract over the 4x and then divide by 2y, and then negative 4x over 2y is negative 2x over y. So that's where that's coming from. So once you plug in the number they give you for dx dt, getting dy dt like that isn't that hard to do, and maybe is a good idea, because it kind of does make things a little bit simpler on the back end. So that's where that's coming from. So then you can plug in the 15 for x. She finds out right now the height is 20 for y, and then you go. We just need units. Feet per second. All right, cool. Thank you. How does that compare to the speed at which we were falling in part 1? It's bigger, right? It's more negative, so you're falling faster. So that makes sense. The longer you're falling, the faster you're going to be going. In part 3, now the base of the ladder is all the way out 24 feet away from the house, so you are really committed to like killing this person up there. Who is 3? Tanika.
So I substituted in x for the equation. I used the one that Rachel did. And so it's negative 2 times 24, which is negative 48, and we don't know why. So we substitute it into the equation. Yes. And since x equals 24, we know that. We can substitute it, and I moved them over. So y squared equals 625 minus 576. That just equals 49. Square root it, and then y equals 7. I substitute it in, and I don't think we can simplify that.
There you go. So at that point, we're going almost 7 feet per second, which is probably not fast enough to kill you, but it'll leave a mark. You can probably go on Google and just say translate 7 feet per second into miles per hour and see how fast that is in units you can understand. Any comments to follow up 25A? Hi, Mohammed. All right. Now, 25C I did not assign, but I want us to talk about it real quick because it gets us back into kind of thinking about angles and stuff. So in 25C, same scenario. All right, you have this ladder leaning against the house. Somebody comes along, pulls the base of the ladder away from the house, still at 2 feet per second. We're going back to the first scenario where the base of the ladder is currently 7 feet away from the house. So X is back to being just 7 for right now. And probably, since we know that, going back to part A, when X was 7, what was the height of the ladder up the house? What was Y? 24. So we don't need to kind of go back and find that again all over again. We can reuse what we already found previously and say, okay, I know when X is 7, Y is 24 because I found that already. We want to find the rate at which the angle between the ladder and the wall of the house is changing. So where is this angle? Bottom, top, or corner? So between who and what? Ladder and wall. Here's the ladder. Here's the wall. There's the angle between them. What's this side? That's the ground of the floor. So not the wall and not the ladder. So between the wall and the ladder, that's up there in the top left corner, that's your theta. And we want to find the rate at which that angle is changing. What do we call that? d theta dt. So our goal is to find out d theta dt. Oh boy. So what trig function do you want to use for talking about theta? Keeping in mind that we know x and dx dt. We do know y, but we don't know dy dt. And we also know the hypotenuse, and that's a fixed value, so we might want to include that. So somebody said tangent. If we're going to do tangent, that's going to be who over what? X over y. Somebody said cosine. If we do cosine of theta, that's going to be, so what's adjacent to the angle? Y over 25. And what's sine of theta? X over 25, right? The opposite side from the angle over 25. Now, with these three options, which is the least bad option for us in this problem? Sine. Why do we dislike sine the least? Because we know x and dx dt, and we like 25 because it's a constant. So we really want to avoid tangent, because then we have both x and y, and they're both variables, and then we have three variables running around, theta, x, and y. Good. Cosine is a little bit better than tangent, because at least we've gotten rid of the x variable, and so we now only have theta and y. But while we know y, we had to do a little work to find it, and we don't know dy dt, unless we kind of go back previous into the problem. Since we know what x is, it would make sense to try to use x stuff. So that's why we're going to prefer to use sine here. So let's kind of then go over here. So all right, sine of theta equals x over 25.
But don't we know why too? So like, wouldn't it not add it?
Yeah, but it's also a variable, and so we would also want to know dy dt. Now, we also know that, so you're right. Based on previous information that we found for ourselves, cosine wouldn't be terrible. If this problem like exists in a vacuum and we don't have 25 part A, then using sine is going to be easier for sure. So this is sine is the best option. Cosine is definitely your next best option. Try to avoid tangent, where you end up with like variables everywhere. So once you're here, what's something we could do to this to maybe simplify things a little bit? Yeah, move 25 over. 25 sine of theta equals x. And then what do we always have to do on these things at some point? Differentiate. So what's the derivative of 25 sine theta? 25 cosine theta. Yeah. Times d theta dt. Right? So you're going to need to get a d theta dt somewhere because that's what you're looking for. And that equals dx dt. Now, you know that dx dt is 2. And you don't know your angle yet. So we got to come back over here and find out your angle. So let's go back to having this be x over 25. And we'll plug in 7 for x. So go ahead, find your angle with your calculator. And probably your calculator is happier in radians, but it doesn't really affect the final answer if you put it in degrees. 0.276. That looks like a radian number to me. So I'll call that radians. What? If it were degrees, I'd expect it to be a much bigger number. Like, I don't know. 0.2837. Well, that's fun. Did anybody get 0.2837 besides Ryan? Did anybody get 0.2760 besides whoever said that? Huh. Check your mode.
Inverse sine of 7 over 25, right?
Yeah, so on your calculator, you would do the sine -1 business that we call inverse sine of 7 divided by 25 in parentheses. And Ryan, can you check the mode that you're in?
I'm in radians.
You're in radians, and you said it was 0.283. So 0.283 radians.
You just do sine of 7 over 25 to get 0.276.
Oh, yeah, that'll do it. Yeah, so make sure you do inverse sine and not sine. If you want to kill the sine function, you got to do its inverse, and that's this thing. That's the second sine button, not just sine. So watch out for that. Once you've got that, you bring it over here, plug it in for your angle, and you can now solve for d theta dt. Because now you can say 25 times cosine of 0.283 times d theta dt equals 2. So go ahead and do 25 times the cosine of 0.283 to make that a decimal. And what is 25 cosine of 0.283? What is it? So you got 0.96. You got. I want to know. Why are you automatically assuming that you're wrong? I don't know either. So go ahead and tell us like this. Are you in radians or degrees? Are you in radians or degrees? Okay. Well, that's bizarre. 24. Did you do just the cosine and not times 25? Okay. So you did the cosine answer. You told me that you forgot the times by 25. See, she wasn't right either. All right.
No, didn't you say 24?
Aha! Aha! Grow some confidence. All right. Usually I don't have to go nanner. You were right. So 2 over 24 is 1/12, and so that's the rate of change of the angle, and our units for the angle is radians. Now, what's weird is even if you got the angle over here in degrees, the rate of change for the angle will still be in radians, because angles are weird. So that's 1/12 of a radian per second. Right? We're doing seconds. What?
You wrote 2.
It was seconds over there. All right, feet per second. Now, don't tell me that you're measuring the angle in feet per second. We don't measure angles in feet, right? Angles are only degrees or radians or revolutions. We never really talk about revolutions because we're not car mechanics. And rates of change of the angle are always radians. Radian is the, well, there's 2 pi of them in a circle. So, like, you draw your circle, and a radian is a measure of how much you have to rotate. So if you break the circle into 2 pi sections, each of those sections is a radian. Degrees is the same thing, but then you cut it into 360. So in some ways, degrees makes a lot more sense. We get radians from the equation for a circle. What? What psycho made this up? Probably Euclid. It's you. Okay. Cool. So, I mean, you have different ways of measuring different things, right? So, like we have for measuring your height, we could do feet and inches, or you can do centimeters and meters, right? Or for measuring longer distances, we can use kilometers or miles. Or for measuring weight, we can use pounds or kilograms. And if you're in physics, you know kilograms of mass, not a weight. Well, shut up. All right. And but like when you go to the doctor's office and you step on the scale, it's either kilograms or pounds, even though they're not the same, measuring the same thing technically. What is it in physics? What's? Well, I know that. So like for measuring weight. It's not, oh, it's newtons. So it's newtons and kilograms. And then what is it, pounds and slugs? I don't know. So, yeah, so different ways of measuring different things. For measuring an angle is just how much you rotate. You measure rotation in degrees or radians. Or revolutions if you're spinning around like a bunch of times. So if you watch figure skating and they talk about like a triple axel, it just means they spun around 3 times in the air. And the triple is talking about how many revolutions they did. 4 and 5. You people.
Yeah.
You were the one who told me. I know, but I didn't know it.
Oh, wait. You give Pings food? Why is your camera shaking? What?
Yeah.
Oh.
Good for you.
So 4, 5, 6. So I have answers to some of these, but I need to go find them. I might print them out, run away, get them from the printer, and come back. So while I'm gone for those 47 seconds, I'll show each other. So I know it's a real danger in this class.